Hello, here in this section, 6.8, we're going to look at something called natural logarithms. We've talked about previously how common logarithms are log base 10 of whatever concept you want. And we use those for the pH scale. In science, we use that for the earthquake scale. Common logarithms certainly have their uses, and so do natural logarithms. Natural logarithms are going to involve a letter E. E is a button on your calculator. E has a particular value. E is approximately 2.71. And at the beginning of this chapter, we watched a video about what is E, where does E come from. E, if you go back and watch that video, is the amount that you reach if you have something with compound interest that's continuously compounding, and no matter how many time periods you divide it up over, what E ends up being is the maximum amount that you will get in terms of interest gained over the course of a certain time period, depending on how many times you are continuously compounding. So the video started off by showing if you invested a certain amount of money, it may have been $100 or $1. It showed that if you did for a whole year and you compounded the interest yearly, how much money you would have. How much money you'd have if you compounded it every 6 months, every 4 months, every 1 month, once a week. And what you found out is if you continuously compounded an infinite amount of times, let's just say minutely, if you continually compounded it minutely, so every minute over the course of a whole year, you don't end up getting infinite money. It ends up multiplying the amount of money that you had by 2.71. So E is the number that represents the most amount you could get back from interest, no matter how many times you decide to continuously compound it. You don't have to understand that about E. It's just something to think about. Financial people would understand more about E, and you could rewatch that video from the beginning of the chapter if you wanted to see it too. So, natural logarithms show up a lot in science. They show up a lot in calculus. They end up accomplishing all sorts of functions, and they appear in all sorts of types of scenarios. The example that we're going to look at is with a spaceship. A spaceship has, all sorts of stuff going on here, and we're going to see something called Ln, and that's what we're going to be looking at today. We found that exponential functions, so y equals b to the x, and logarithms, so x equals log base b of y, are inverses in the previous section. Today what we're going to learn is that the natural log is the inverse of what's called E. All right, natural logs have a base E. The good news is that natural logarithms work just like logarithms. So the same properties apply. But what's important to note is that when we used to look at logarithms and you didn't see a base, we knew that there was an invisible 10. What we're going to see now is something called Ln. Ln has an invisible base as well. Its invisible base is E. And they used Ln so that it can be different than log. Ln stands for log natural. All right. So when it comes to simplifying logarithms, this is going to be a review of the properties. Natural logarithms work the exact same way. Let's review some of our properties. The properties were, if we have log of x plus log of y, or anything for x and y, so two logarithms that have the same base that we're adding, you multiply the inside pieces. If we had two logarithms that have the same base and we are subtracting, we could set it up as this one logarithm with division. And then the other rule was if there was some letter out front, or some constant out in front of the logarithm, that constant could become the exponent on the inside of the logarithm. So let's simplify some natural logarithms. First thing I want to recognize is that due to this subtraction sign, I'm going to have one natural logarithm with division. The 15 is going to go on top, and I can also carry over this squared to be right there. And so we get natural log of 15 squared over 75. And we can then simplify the inside part as well if we want. 15 squared is 225. 225 over 75 gives us 3. So this ends up being the natural log of 3. Now, the natural log is a button on our calculator. If you look at your calculator, there's the screen. Natural log is a button right next to the log button. So there's on, here's STO. If the fourth button up is log, the third button up is natural log. So you could simply type in ln of 3, and it would give you an answer. It's a decimal, and we'll learn more about how to use it coming up. Here's another scenario. We're going to condense it down to one natural log. I see I've got a subtraction sign, so I know there'll be some division. A is with a positive sign. It's invisible, but that means that A is going to go up top. This is also with a plus, so this 1/3, which will become the exponent on C, due to this plus sign is going to be multiplication up top with the A. So this would be C to the 1/3 power. Now this 2 can go with the B, but due to this subtraction sign, it will go in the denominator. So this natural logarithm was started off as 3 pieces using the properties of logarithms that we learned previously. We can combine it into one natural logarithm, and I'm going to erase this and kind of show it to you again. Anything that has a plus sign, whether it's invisible or not, multiply together. So that's why we see those 2 terms up top. And any term with a subtraction sign goes to the division. So when I go to condense this one, I see that I've got a subtraction sign, so I'll know there'll be division. And then it's the 3. And then this is 3 to the 5th power. And 3 over 3 to the 5th would simplify to 1 over 3 to the 4th. And 3 to the 4th is 81. So that's using properties of logarithms to simplify natural log expressions. We'll need those skills coming up to help us solve equations. We're now going to solve natural log equations, which will build on to our solving logarithmic equations from 6.7. Both of these here are going to require loop and swoop. They'll work just like they did with natural logs or with regular logarithms. We need to figure out what the base is, and we can also use some properties to make this a little easier. Anytime there's a exponent, you can write it out front. So this is 2 times the natural log of x minus 3. Before I'm ready to do loop and swoop with this e, we can divide both sides by the 2 to get our natural log piece by itself. Now we're ready for loop and swoop. We have e squared is equal to x minus 3. Then when I add 3 to both sides, we'll get that x is equal to e squared plus 3. Now you might be wondering, well, what is e squared plus 3? Remember that e is just a number. We talked about that. That's about 2.71. A lot of times you'll leave your answer just like this instead of switching it to decimal. But if we wanted to switch it to the decimal, we need our calculator. If you look at your calculator, above the division button, so if this button is division, above it you'll see in a different color a little e. That e is the e that we want. So if I wanted to figure this out as a decimal, on my calculator screen, I'm going to need to push second, and then I'm going to need to push the division button, and it'll give me an e. Then I'll square it and add 3. And when I do that, so if I do e squared plus 3, it gives me an answer of approximately 10.4. So if this throws you off, understand that this is just a number. It's approximately 10.4. But to avoid decimals and rounding, we'll typically leave e left over as a part of the answer. Let's solve another one here. Now, one thing about the properties is that there's a lot of attention to detail that needs to be had. This 2 can actually not go up front because it's not to both the 2 and the x, it's only to the x. This problem is different than this. If it was written like that, we could bring this squared out, but it's not. So we're going to have to leave it and address it here in a moment. We can, however, go ahead and divide both sides by 2. And then we'll have natural log 2x squared is equal to 1/2. And we're ready for a loop and swoop for our base e. So we'll get e to the 1/2 is equal to 2x squared. We will then divide both sides by 2 because I'm trying to solve for x. So I get x squared is equal to e to the 1/2 power, all divided by 2. The next thing we'll need to do is take care of the fact that x is being squared, which for us means we will need to square root both sides. And we'll get that x is equal to plus or minus the square root of e to the 1/2 power, all divided by 2. So this might seem very intimidating to you because you don't know what ln really is or what it's about. Now we've got plus or minus and the square root of e to the 1/2 power divided by 2. This can all seem very intimidating and very difficult, and it's normal to feel like that. Natural logarithms and logarithms are fairly complicated. They show up in complicated stuff, like rockets blasting and going into space. So it's not necessarily an easy concept. It does take a lot of practice and understanding to make some progress with. You don't have to be comfortable with fully understanding like what all this means, the square root of e to the 1/2 power divided by 2. We just have to be able to go through the different steps and solve these. You do need to be comfortable with your loop and swoop. And then coming up here, we'll be using drop, log, and roll. And what this does is it allows us to take scenarios that were logarithms, and loop and swoop allows us to take scenarios that were logarithms and turn them back into regular equations. Drop, log, and roll allows us to get x out of the exponent. So those are the 2 keys, right? We definitely need to understand loop and swoop, and we definitely need to understand drop, log, and roll. And you can go back and check out the previous videos to help understand those concepts. Now for this one, we need to solve for x, but x is in the exponent. So we're going to need to use drop, log, and roll. What drop, log, and roll is it gives us an opportunity to get the x out of the exponent, because we drop the base b with logarithm, and then the x and y switch places. And now x can be solved for. So that's what drop, log, and roll is all about. Loop and swoop was when you are already in a log, so log base b of y is equal to x. It's where you take the base, raise it to the opposite power, and set it equal. So this goes from logarithm to exponent. Drop, log, and roll goes from exponent to logarithm. So taking a look at this one, before we are ready to use drop, log, and roll, we need to subtract 2 from both sides. And then we need to use division, because we need to get that e all by itself. So we have e to the 2x power is equal to 7 over 2. And now we'll need to use drop, log, and roll. But I'm going to use ln, because ln has that invisible base of e. So when you see me using ln, we know that the base is e. So we dropped down the base. I'm going to go ahead and put it back there for us. Even though you don't have to, these switch spots. And then we can finish solving for x by dividing both sides by 2. So x ends up equaling the natural log of 7 over 2. All of that divided by 2. These answers will look very strange. You'll definitely need to know how to do them, because there's no way to guess that answer based upon the original setup. You will need to be able to take the steps to find that. If you're wondering about double checking these, you can double check them. It gets a little tricky to do that. But if you were to type it in successfully, if you were to go to your calculator and up in the exponent, type in natural log of 7 over 2, all of that divided by 2, just like that, you would reach the answer of 14. So let's try another one. And once again, these are very messy, and that's okay. These are the hardest types of equations that we solve. So we add 8 and add 8. We have e to the x over 9 power is equal to 14. And now we're ready for a drop, log, and roll. But in this case, I'm going to use natural log, ln, because it has base e. These two will switch spots. So we'll get that the natural log of 14 is equal to x over 9. And then we multiply both sides by 9 to get that this answer is 9 times the natural log of 14. And you could double check that one as well on your calculator. Let's take a look at an example where we can use natural log. A spacecraft can attain a stable orbit of 300 kilometers above the Earth if it reaches a velocity of 7.7 kilometers per second. Let's first talk about just the way that orbiting works in general, because it's very interesting. When you have a planet, so I'll just draw Earth here, orbit is when you travel around it in a circle like that, whereas your satellites do it, the moon orbits around the Earth. Depending on how far away you are from the Earth, your circle will look different. Now, the way that orbiting actually works is you have to reach just the right speed in order for your orbit to stay steady. And here's some examples of what would go wrong if you didn't. If you send something up into space and you're going too slow, it'll slowly fall back and then crash into the Earth. However, If you started it and you're going too fast, you'll just fly off into space. But if you find the exact right speed, you'll essentially be continually falling around the Earth in a circle forever and ever. And that's what orbiting is. And depending on how far away you are from the planet, you have to be going a different speed to make sure that you're orbiting correctly. As you can imagine, that's very complicated to understand and work with. That's why all these equations have been so complicated, because natural logarithms and logarithms help us accomplish complicated things. So a spacecraft can attain a stable orbit 300 kilometers above the Earth if it reaches a velocity of 7.7 kilometers per second. The formula for a rocket's maximum velocity in kilometers per second is v equals, and then we have that equation with a natural log in it as well. The booster rocket fires for t seconds, and the velocity of the exhaust is c seconds, or c in kilometers per second. And then the ratio of the mass of the rocket filled with fuel to its mass without fuel is r. Right, and so what r ends up doing is it changes, right? Because when you first take off from the ground, if we think about from a gas tank perspective, you are totally full on gas. But then as you get higher up into the air and you've been shooting your rocket fuel, you'll have a little bit less gas in it, right? And so how much weight the rocket has is constantly changing. It's heaviest right at the start because it's totally filled with fuel. It starts to get lighter as you fly up into the air because you're burning off the fuel. Lots and lots of factors that go into space travel. It's very interesting stuff if you are interested in the numbers and the math. Suppose the rocket shown in the photo has a mass ratio of 25, a firing time of 100 seconds, and an exhaust velocity as shown. Can the spacecraft attain a stable orbit 300 kilometers above Earth? So that may seem very complicated, but all we're going to be doing here is replacing values in our equation with what they tell us. And here's how we need to do it. Let's just break it down piece by piece. We're trying to answer, can it attain stable orbit of 300 kilometers above Earth? So in terms of our equation, which is v is equal to negative 0.0098 t plus c times the natural log of r. If we're going to be orbiting 300 kilometers above Earth, we need our velocity to be 7.7. So we're going to determine, is 7.7 equal to our equation when we plug in the different variables? They told us that our time was 100 seconds. They told us that our c is the velocity shown. So we have 2.8. Here's our c right there. And then the natural log of 25, this is just going to be a button on our calculator. All of this is just going to be typing it in. So if our rocket has these components to it, a firing time of 100 seconds, a velocity of the rocket's force as c of 2.8, and then the weight ratio of 25, if we type all this in on the calculator, we get a speed of this rocket overall going 8.0 kilometers per second, because that's the velocity unit that we're in. So what this tells us is that the rocket does have the capability of reaching the velocity of 7.7 kilometers per second. Is it going too fast to stay in orbit? Is it going to launch off like this blue line? I don't know. But we do know that it does have the capacity, if they maybe took away a little bit of the force or something like that, to at least make it up to the 7.7, because theirs is going 8 approximately kilometers per second. So it does have the capability of going into orbit. And that's what we'd want to find out. Because if we're too powerful, we can bring that back a little bit. But if the force that we plan on launching with isn't enough to reach that 7.7, it wouldn't be able to stay in orbit, and it would crash back down. Complicated stuff, right? Fancy formulas, natural log. And remember that that LN button is just a button on your calculator. It's down here. We can do a lot of stuff with this. You're probably still very confused by the types of equation solving that we've been doing. We're going to have a review that has a video with it that's going to help us understand. And the homework also has all the different steps shown to get us used to the various equation types that we can see with logarithms.